Good evening, everyone. I'm audible. Hello.
Yeah,
Am I
you're
audible
audible.
to everyone? Okay.
Yeah, yeah,
So
you're
we'll
audible.
wait for just few minutes for others to join. Then we'll start. Okay.
Sure.
Yeah. Okay. I think let us start. It's past 5 minutes. All right. So I think I am visible right now. Hello.
Yes, sir.
Yeah. Okay. So very good evening,
Yeah, you're
everyone.
visible.
Yeah. Okay.
Good evening.
Yeah. So today, my name is Varnit Kapoor, and I'll be taking up the. Yeah. So okay. So my name is Varnit Kapoor, and I'll be taking up the tutorial sessions for this course on the NPTEL, that is computational fluid dynamics using finite volume method. So currently I am pursuing my PhD at IIT Delhi. Okay. So that's my introduction. So I see that four of you have joined: Madhav, Bhavan, Sean, and Jen. So I think we are for now. Maybe others will join with time, due course of time. So is anyone from IIT or among four of you? Any of the IIT? Yes.
No, no,
Okay.
I'm not.
Yeah. Please go ahead, Bhavan.
No, Varnit, like to your replies, I'm not from IIT. Like,
Okay. 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 So
I'm,
you all are a bachelor's or master's or from industry?
yeah, I'm like currently, my name is Bhavan, and I finished my graduation at JSS Academy, and post graduation, I'm working as a CFD engineer at General Motors, and that is
Okay.
placed in Bangalore.
Okay. Okay. Great. Great. Thank you, Bhavan. And Madhav.
Yes, sir. I'm right now in third year of mechanical engineering, pursuing it
o-
from DTU from Delhi
Okay.
only.
Yeah.
And yeah, I worked like I have a little bit of experience in Formula Student. I'm part of Formula Student team. So we basically design race cars, and I'm in aerodynamic department of that team.
Okay.
So
Great.
yeah,
Great. Okay. What about Sean? Sean, are you there? Acha, okay. I don't have a mic. I'm currently pursuing third year BE. Okay. All right. Thank you. Jayant. Jayant, are you there? Okay. No problem. So I hope you all have seen the course videos for week 1 as well as week 0. The assignment was floated. Have you guys seen the lecture videos by the prof? Okay, no problem, Jay. You can raise your hand if you have seen. There's a raise hand option. If you guys have seen, I'll get to know that okay, you have seen the lecture videos, and we can proceed accordingly. And if you have not seen the videos so far, so don't raise your hand.
yeah, I've seen.
You have seen. Okay. Okay. All right.
Varnit, from my side, I've seen my introduction video. Other than that, I'll make some time from today, like to see lecture videos. Actually.
Okay. Okay. No problem. Actually, my point is that because as the course will proceed, and this is a higher grade level course, okay, seventh level course, which we say in for PGs. So as the course will proceed, so the thing is that it will pile up on. So I want that you guys continuously see the videos. It's okay if you have not seen for this week, no problem. So is there any because we have to submit the assignments as well. I don't know like how many of you have you going for the test as well towards the end. But assignments, if you do, that will be really, very helpful for you all. So, is there any expectation from what kind of expectation you guys are having from the course? Like, what actually you want? So, some of you have seen the videos. So, you have got an idea that in the week 1, as well as week 2 videos, I think have been floated as well. But we will currently focus on week 1 video for this week, whatever the content is there, the question related to that and the doubts if you have. So that will also be helpful to you guys when you will watch the video. So you can ask me the doubts. So any like expectations from you guys that like I want this kind of thing to go on in the course or some another thing. Any of the expectation or whatever idea you have or why you have joined this course. What found interesting in this course that you opted for?
Like,
Yes, yes, Bhavan, go ahead.
yeah, Varnit. Like, basically, me started my career as a CFD engineer in several institutions. Like, in my graduations and all, we got to know like what CFD uses. Is it a cell-centered method and all? And finally, like on a overview, we got to know it's like finite volume method we use overall for a CFD, and we solve the simulations in that way. Actually, Navier-Stokes, any of those equations. So
Yes.
like we have got some little overview and we are trying to get digging deep into the subject, understand the overall concept in a wider way, in a better way. So this is the main reason that I opted actually. So we'll
Oh,
get a very good exposure. We can only talk like oh this and all. It is the finite volume method, cell center method. So this is how it solves. We need a digging deep knowledge to understand better way. So this is my
correct.
why I opted is the same like to get the more knowledge CFD solving by finite volume method. This is
Correct.
why I
Correct.
selected.
Okay. Great. Great. Thank you, Bhavan. And any
Thank
other
you.
one? Yeah, Madhav, Sean,
Yeah, so
James. Yeah.
basically, I want to research a bit and learn about computational thermofluids in general.
Okay.
And I saw it as a domain certification of NPTEL. So in that, I have basically studied the basic CFD from Anderson already. So
Okay.
now, so the next step for me, I thought, and after discussing it with my seniors, I thought it would be the finite volume methods.
Yeah.
After studying it and studying a bit more about the mathematics, all the numerical methods and all, uh,
Yeah.
I can just get into this research side in a really good way, and I can basically build up my foundations using by like with the help of really good professors of IITs. So that was what
Yeah.
my initial thought was behind joining this course.
Okay. Great. So I think that at bachelor's level, this course is not taught. Even basics of CFD is not taught at the institutes. I don't know about others. Like at IITs, it's been taught, but I don't know. Like for other colleges,
Yeah,
it's taught.
in my university as well in DTU, the basics of CFD is taught
Okay.
from that Anderson book. So like the basics of discretization and graph that grid transformation and some
Okay.
general models.
Okay.
But and that I know a bit, but I just want to learn a bit more about finite volume methods and just go a bit deeper pretty early on only
Yeah.
because like my second year is completed and from the third year I want to like basically fix my attention onto the subjects and topics which I have to research in like in the coming time. So that is it.
Yeah. Yes. Yes. Okay. Great. Great. And like CFDs, it's a like very wide variety of branch, and it's a commercial usage as well as Bhavan is working in the industry as well. So many commercial softwares are available, open source softwares are available for solving these discretized equations, basically the Navier-Stokes equations and whatever kind of flow it has, compressible and incompressible. So if you have watched the videos of lecture one, you might have seen that Prof has discussed about the general governing equations for both compressible as well as incompressible flows. Okay, so pretty much basic things that just they are deriving the governing equations. And if you see the assignments also, so assignment zero is just basic fluid mechanics, and assignment one is basically the questions framed on whatever equations have been derived. So what different terms mean for a different equation. So basically you should have an idea that what an equation says, what each term of that equation says to you. Okay. So that's very important. Okay. So we will I think it's a 2 hour session. So definitely uh, we will take up the basics of the equations as well as I'll take up with the questions from the fundamentals of fluids related to CFT as well. Okay. So I know people are here from industry, bachelor's, master's, PhDs, and anyone can join the NPTEL courses. So let's start. So 15 minutes have passed, and that's all. So let me share my screen, and I'll
Varnit,
use, yeah, go ahead.
small question. Sorry to disturb you.
Yeah.
Yeah, Varnit, like regarding the assignments that you said, like for the week 1 that we have to, for the questions given, we have to write physically and scan it and send. That is how it is done.
Actually, you might have got the mail regarding that. So there is the options you have to select at week 1, week 0, you go assignment part. So there are 10 questions, MCQ. type. So you have to choose the option, and I guess that's the way to submit the same thing. There is no
Sure, sure.
option to upload anything so far.
Oh,
So any other
okay.
student can also tell, like Madhav, have you solved the assignment?
Yeah. So there's basically a PDF in which all the questions are given and the
Yeah,
options are also given. And on the basically you have to first of all get the right option, and then you have
yeah,
to select it on the portal and then
yeah.
simply submit the test.
Yes, that's the way. Yeah. That's fine. Because there's nothing to scan, nothing is there. And you will have an
Okay.
those who have registered for certification, you will, I think, have to go at an exam hall at towards the end of the course and give the exam. That's the thing.
Yes, I had a question regarding exam that will it be
Hmm.
the MCQ type an exam or it would be some subjective?
See, that's depend on prof how they have framed the exam. So we are also not told about that thing. So that solely depends on the prof and how they floats and the NPTEL team. So maybe you can ask mail the NPTEL team regarding that as well. And if I get a
Okay.
chance, I'll also ask them.
Okay.
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 Okay. All right. So let me share my screen. So so I hope my screen is visible now. Okay. So one thing, let me tell you that all the session recordings and the notes which I'll be writing will be available to you all. So session recordings I'll be posting on a YouTube. Okay, so there I have made a YouTube channel, and you can see all the videos for every lecture tutorials that what we are discussing, and all the PDFs of the notes I'll be uploading, and maybe the NPTEL team will share with you guys the resource folders. Okay, even if you get any doubts, so you can ask me anytime after the class or post it into the discussion form. I'll definitely get back to you or any of the members from the NPTEL team. Okay. Don't hesitate. And during the course as well, please don't hesitate when I am teaching in the class. You find any doubts, please don't hesitate. You can unmute and ask at any point of time. So let us start. So let me just go with a preview of what has been done in the tutorial videos. Sorry, lecture videos. Because some of you might have not seen. So I'll just give a glimpse of each and every equation once again, and then we will solve the question based on those equations. Okay, and then you have to solve the assignments on that basis. Okay. All right. So assignments are solely for the students. You have to only solve. You can ask me any quirky doubts if you have, but I cannot solve the assignments in the class. Okay, please take care of that. All right. So generally in the week 1, the prof has discussed about the governing equations of fluid flow and the heat transfer. And the governing equations of the fluid flow basically represent the mathematical statements of conservation laws of the physics. So let me write it down. Governing. And you guys have also the notebook and pen. You can pen it down. And when I'll give the questions, I'll give few minutes to solve so that you can also come up in the classroom itself. Governing equations. I hope whatever I'm writing on the screen is visible.
Yeah, is it?
Okay. Of fluid flow and heat transfer. All right. So there are basically different kind of equations. One is the mass conservation, momentum conservation, energy equation. Okay. So there, the mass of the fluid is conserved. Mass of fluid is conserved. Next, rate of change of momentum equal to the sum of the forces on a fluid particle, which is nothing but a Newton's second law. The rate of change, just a second, yeah, of momentum equals the sum. of the forces on a fluid particle. On a fluid particle, that is nothing but Newton's second law. Newton's second law. And next is the rate of change of energy, conservation of energy, which is basically first law of thermodynamics, which says rate of change of the energy is equal to sum of the rate of heat addition to the system and the rate of work done on a fluid particle. Okay, right? Rate of change of energy is equal to the sum of rate of heat addition and rate of work done on a fluid particle. That is nothing but first law of thermodynamics. Okay. And the fluid is considered or regarded as a continuum, okay, for the analysis of fluid flow. So that at macroscopic length scales, that is 1 micrometer or larger, the molecule structure of the matter and the molecular motions may be ignored. Okay, when we consider the fluid is having a continuum behavior. So we describe the behavior of the fluid in terms of macroscopic properties such as velocity of the complete fluid, pressure the complete fluid is experiencing, what is the density of the complete fluid, and the temperature experience, and their space and the time derivatives as well. And these may be thought of as averages over, like you can say, suitably large number of molecules. When we are saying it's a continuum, showing a continuum behavior, so it is for large number of molecules. And a fluid particle or a point in a fluid is then the smallest possible element of the fluid whose macroscopic properties are not influenced by the individual molecules. Are not influenced by the individual molecules. Okay. So let us come to mass conservation in three dimensions, which has been discussed the first equation. Mass conservation in three dimensions. So what does mass conservation says is that rate of increase of mass in any fluid element is equal to net rate of mass flow into the fluid element. So whatever is going inside, whatever is going outside of that element is equal to net rate of increase of mass inside that fluid element. Okay, let me write it. Rate of increase of mass in fluid element is nothing but net rate of flow of mass into fluid element. Okay, just the basic. So net rate of increase of mass in fluid element is nothing but, if you express it mathematically, that is density into volume, that time derivative of density into volume, because it's a rate. It's a rate of the mass. So that is dou of dou t density. Suppose you have a fluid element which has nothing but, let me make the first fluid element. So suppose this is a fluid element. The directions are given in the sense that this is Z, this is Y, and this is X. Okay, or let me make it bigger. Z, Y, and X direction. These are the three directions. And the elemental dimensions are like this. Dou X, delta X. This is nothing but dou Y. And this is dou Z. So these are the elemental dimensions. Okay. And suppose this center point have the coordinate x, comma y, comma z, center of this fluid element. So this is nothing but a fluid. If someone has joined. All right. This is nothing but fluid element. This is a fluid element. Okay. So I request you all that you all kindly join on time so that you are in the coordination, the flow of what is going on. Okay. And be regular to your classes as well. So suppose any property, suppose there is a pressure at the center of this fluid element. There is a pressure at the center of this fluid element. So what will be the pressure on the east face? What will be the pressure on the west face? So that is nothing but pressure at east face. Property of pressure at east face is nothing but pressure at center, that is P, plus by Taylor's expansion, dou P. Let me make it a small pressure P, and small pressure P at the center, dou P by dou X into, because we have considered that right side, upside, and the back side are in positive. So these are the positive directions. Positive. Okay. So that means towards this east face, this will be delta x by 2. This dimensions will be nothing but delta x by 2. Similarly, on the west face, that will be P plus dou P by dou X into minus dou X by 2. Minus dou X by 2. Okay. So I was saying about the rate of increase of mass in the fluid element, coming to the mass conservation, the rate of increase of mass in fluid element is time derivative of density. Density is rho into the dimensions, that is volume, dou x dou y. So the volume of this small fluid element is dou x into y into z, that is dou x dou y to z, which is nothing but, if you take out density is constant for this fluid, so that is dou x dou y dou z. Dou x dou y dou z. Okay. Now we need to account for the mass flow rate across each of the phase. Mass flow rates across each of the phase. So east, west, north, south, and front and back. Okay. That is nothing. From the Taylor expansion, you can get that thing. And Prof has also derived that thing. So I'll give you a hint once again, a recap that suppose at this point, when the mass is entering into, so mass is entering from this phase, mass is exiting from this phase. Okay. So by Taylor's expansion, you can write rho u plus dou by dou x of rho u into delta x by 2. Delta x by. So we consider up to first term. Higher order terms we can neglect. Okay. Higher order terms we can. Similarly, mass will enter from each and every phase. Each and every phase. So we take. So mass will enter from here and exit from here. Then mass will enter from front phase and exit from back phase as well. So everything has been derived by the prof. So when you come out to the last equation, the rate of increase of the mass inside the element is now equated to the net rate of mass that is flowed into the element across each of the phase and exiting from that element. Okay. That gives you a final equation of mass conservation, that is dou by dou t. Let me write the final equation. I'll be just giving the recap of what has been done all the three lectures. Dou by dou t of rho plus dou by dou x of rho u velocity in the x direction. If we assume dou by dou y of rho v density velocity in the y direction plus dou by dou z of rho w, that is nothing but equal to 0. Or in more compact form, you can write in the vector notation dou rho by dou t plus divergence of rho u is equal to 0. So that is nothing but unsteady three-dimensional mass conservation, or you can say a continuity equation at a point in a compressible fluid. Why compressible fluid? Can anyone tell me why I'm saying it is a compressible fluid? Yes.
Yeah, because there is a time derivative with density. So that's why.
Yes. So density is not constant
Yeah.
uh, for the fluid. Okay.
And sir,
That.
I had another doubt.
Yes. Yes.
Basically, Prof has coined the term rho u as momentum in the lecture. So,
Yes.
means does it signify the momentum term, the rho u? Basic momentum at the center is rho u.
So yes, you can say that thing as well. That rho u is termed as a basic momentum equation, basic momentum term. Okay. So
Mhm.
he has also explained that why it is called and each and every time if you have seen the video. Yeah, you can see. All right. Okay, so this is a compressible equation because of the density is not constant in the system. So I'll write it down here. It is a very important equation. So all these three equations has been done by the starting of the course because these are the heart of solving and discretizing these equations for solving the fluid flow, whatever happens with time. So it is the unsteady, three-dimensional mass conservation. So I'm not going into the derivation because already that has been done in the lecture videos by the prof. Continuity equation at a point in a compressible fluid. In a compressible fluid. Okay. And when we are saying that it is an incompressible fluid, that means density variation will be neglected because now in fluid is incompressible. It cannot compress. That means the first term, that is a local portion, is nothing but ignored because density variation is not taken. So for incompressible, therefore, for incompressible fluid. Density is constant. Rho is constant. Therefore, this implies dou rho by dou t is equal to 0. Therefore, you can say dou rho dou of u, because rho is constant, automatically this rho can come out from each term. This rho can come out from each term, and that will go on the right hand side, will become 0. That will become 0. So that is why dou u by dou x plus dou v by dou y plus dou w by dou z equal to 0. That is nothing but someone is trying to join. Okay, no one is there. Is equal, or in index notation you can write divergence of velocity u, general velocity u is equal to 0. Equal to 0. Okay. Now, any doubts still here to anyone?
Yeah, so basically
Yeah.
this incompressible flow equation is for steady and unsteady both type of flows.
The compressible one is for
This incompressible one, this last one equation, this is for both steady and unsteady
no
flows.
steady. Unsteady, how it will come? If unsteady is there, then this term cannot be 0.
No, the niche wali equation for the incompressible flow, this equation,
Yes, yes, yes.
it is for both types of fluid flows.
Yes, for incompressible fluid flows. Yes. Okay. I think someone is trying to join, but uh, all right. I don't know who is trying to join. Okay, let's come to the next part. So, rate of change of any property of for a fluid particle is very important, because the momentum and energy conservation laws make statements that regarding the change of properties of a fluid particle. Okay, so each property of such a particle is nothing but a function of positions as well as time. So pressure, suppose the property velocity is there, that can change with respect to positions as well as with time. Okay? So let there is a property phi, okay, which is per unit mass denoted by phi. So the total or a substantial derivative with respect to time for the following fluid particle is written as, let me write the first heading, rate of change following a fluid. Okay, no one is there. All right. Following a fluid particle and for a fluid element. Okay. So I'm saying phi is any property, okay, that is denoted by property per unit mass. Property per unit mass, and the total or substantial derivative of phi, that is nothing but dou phi by d phi by dt. Capital D phi by dt is nothing but written as dou phi by dt dou t plus. Now the property phi is nothing but function of phi is function of x, y positions as well as with time. So it once it vary with the time, another time it vary with the positions. But position itself vary with the time. So dx by dt. Similarly, dou phi by dou y into dy by dt plus dou phi by dou z into, from the partial chain rule, partial derivative rule, dz by dt. Okay. All right. Now we know that these terms, this term, this term, and this term is nothing but velocities in x, y, and z direction. X, y, and z direction. So I can write it as dou phi by dou t plus u into dou phi by dou x plus v into dou phi by dou y plus w into dou phi by dou z. Okay, dou phi by dou z. So d phi by dt, that is nothing but a substantial derivative, defines the rate of change of any property phi per unit mass. And as in this case of mass conservation equation, now we are interested in developing equation for rate of change per unit volume. Rate of change per unit volume. Okay, so rate of change of the property phi per unit volume. When you are saying per unit volume, see, phi is per unit mass, but you want it per unit volume. So you will multiply it with density rho. So any change will be written as d phi by dt into rho, because it is per unit mass. Per unit mass, mass is nothing but mass density into volume. Density into volume. Now you want per unit volume. Per unit volume. So that is why you multiply it with density. Is it clear? That why I'm multiplying it with density?
Yes, yes.
Okay. So it can be written as rho into d phi by dt. Rho into d phi by dt is nothing but rho. Multiply the right hand side with rho as well into dou phi by dou t, and in the vector notation u of grad phi. Grad phi. Okay. U of grad phi for the above equation. This is per unit mass. Per unit mass, and this is per unit volume. Per unit volume. Per unit mass, per unit volume. Okay, so the mass conservation equation contains mass per unit volume, that is density. You know that density is there as the conserved quantity, and the sum of rate of change of density and the convective term, that is dou rho by dou t plus divergence of rho u, is nothing equal to zero, is nothing but the mass conservation equation. Okay, and similarly for any property phi, you will just take dou by dou t of rho phi plus divergence of rho phi u. Rho phi. Okay. So I can write the relationship of the substantial derivative of phi in the form dou of dou t of rho phi. Let me write it as a subheading. Substantial derivative of phi shall substantial derivative of phi is nothing but everything has been derived. I'm repeatedly saying everything is derived in the lecture videos. So please go watch the videos. I'm just giving a brief. So I hope that it should not jump out of your head. I'm just giving a recap. So please always come before watching the videos to class. Dou by dou t of rho phi plus divergence of rho phi u, rho phi u. See this term I am only writing as this term. Okay. How? This is nothing but the partial derivative, that is the local part, and this is the convective part. And here also, I will write the right hand side term I will write from here. Right hand side term I will write from here. Now you see is equal to rho of dou phi, rho of dou phi by dou t. Okay. See, This I will expand now. This row I have taken out for density constant. Now you see the row of dou phi by dou t plus. First, I will do a grad of rho phi and take out u outside. U dot grad phi plus. Then next time I will take out phi outside. Dou rho by dou t plus divergence of rho u, which is nothing but equal to rho of dou phi by this term as it is. This term as it is. All right. So what does each term depicts? That rate of increase of phi of a fluid element plus net rate of flow of phi out of the fluid element is equal to rate of increase of phi for a fluid particle. Rate of increase of phi for a fluid particle. So rate of increase of phi for a fluid element is net rate of flow of the out of the fluid element of phi out of the fluid element is second term, which is nothing but equal to the rate of increase of phi for a fluid. The substantial derivative itself. Substantial derivative itself. Okay. Now we will come to the momentum equation in three dimensions. Momentum equation in three dimensions. So to construct the three components of momentum equation and the energy equations relevant for entries of phi and the rate of change per unit volume, you can say, let me write it down. Momentum equations in three dimensions. So mass conservation is done. Why this phi was done by me or by the prof is because that you know that how the substantial derivatives play a role, because there are a lot of things in a general momentum equation. Okay, lot of terms are there in the general momentum equation, and you want to know that how this term is bifurcated in different local as well as convective parts. Local as well as convective parts. So local part is this that is changing with time, and this is changing with space, convective portion, convective or advective. You might have read this in your basic fluid mechanics as well. So momentum just is nothing. Momentum equation is nothing but Newton's second law, as I wrote in the starting of the lecture, which states that rate of change of momentum of a fluid particle is nothing but equal to sum of all the forces acting on that fluid particle. Rate of increase of momentum of fluid particle is nothing but sum of forces on fluid particle. Okay. So rate of increase in x, y, and z momentum equation will nothing but substantial derivatives. Okay, substantial derivatives. That is dou. Now you will write this property phi. See, this property phi, this property phi will now change from phi to u, because there is a u term in x momentum direction. There is a v term for y direction, w term for z direction. Okay, for each and every direction, this property phi will change. So that will be represented by rho into substantial derivative of du by dt. That is on the left hand side. Rate of increase of the fluid element is nothing but rho into du by dt for x direction, rho into dv by dt for y direction, rho into dw by dt in for z direction. So left hand side will be written like this. And some of the forces on the right hand side are nothing but the body forces. Body forces are nothing but gravity, centrifugal, Coriolis, and electromagnetic, plus surface forces. Surface forces, which is nothing but pressure forces and viscous forces. Pressure forces and viscous forces. Any doubts still here? I hope you are able to understand that. What's the foundation? Any doubts?
Yeah. No,
Yes,
no.
no doubt. Other students, Bhavan, Nitesh, Sunil,
No, as of now, he's okay. Yeah, very good.
uh, is it clear till here?
Yeah, yeah.
Okay. Now, so I'll write a momentum equation for one direction. Everything has been derived as I repeat again. So x direction momentum equation is nothing but rho, the left hand term, du by dt is equal to dou by dou x of pressure term. Pressure is a surface force plus the viscous portion tau xx on the normal x direction plus the shear stress is acting in the y directions as well. To tau yx by dou y plus dou of dou z of tau yz plus any other source terms in x direction. Similarly, you can write for the y as well as for the z. So these source terms can be a compromise of the body forces like gravity. So for x direction, gravity will be zero. For x, it will be zero. But for z direction, the gravity x downward. So you will write it as minus rho g for z direction. For z direction. All right. Now let's come to the energy equation. Energy equation. So momentum equation is understood. Mass conservation is understood. Let's come to the energy portion. Energy equation in three dimensions. Hello? Okay. Yeah. Energy equation in three dimensions. Energy equations in three dimensions. So energy equation is nothing but derived from first law of thermodynamics, which states that rate of change of energy of a fluid particle is equal to the rate of heat addition to that fluid particle plus the rate of work done on that fluid particle. So rate of increase of energy of fluid particle is nothing but net rate of heat added to fluid particle plus net rate of work done on fluid particle from first law of thermodynamics. So again, rate of increase of energy, that is nothing but rho of that property phi will change from phi to energy E. This left hand term will be now rho of dou E by dou T. And the right hand terms will be derived accordingly based on the heat added and the work done on the fluid element. Heat added and the work done on the fluid element. So I'll just write it down, the equation directly which has been derived. So let me just write it down. It's a big equation. So rho of dou E dE by dt is negative of divergence of rho u plus now the other term comes for, you can say, or let me give the final equation with respect to the enthalpy or internal energies. That will be a much better idea. But okay, let me give a midway equation as well. that's derived in the lecture. So dou by dou x of u of tau xx plus rho of dou by of u tau yx plus dou by dou z of u tau in zx. Okay. This is for x direction part. Similarly for y direction part plus dou by dou x of v tau xy plus dou by dou y of v tau yy plus dou by dou z of v zy zy. Okay. Similarly for z direction, dou by dou x of w tau xz plus dou by dou y of w tau yz, okay, plus dou by dou z of w tau zz, normal component, plus these are the viscous terms, those are the convective terms, plus divergence of k, that is conductivity from the Fourier law of plus source. Okay. Now each and every term again can be written, and in terms of enthalpies that has been derived the final equation. So only the term which change is uh, rho h naught will come on the left hand side plus divergence of rho h naught u will come plus the other right hand side terms will be as it is. These terms will be as it is for the pressure terms as well. Okay, for the viscous terms as well. Now to link because now if you observe we have so many equations and so many variables. Okay, but variables are more than the number of equations present. Variables are more than the number of equations present in the system. Okay, so that is why we want equation of state, thermodynamic equations of states. Okay, equations of state to solve them. So equation of states are nothing but how you relate your pressure or any other variable, temperature variables with, if you use rho and t as a state variables, we define the equation of states for pressure and internal energies, specific internal energies. So equation of state, that is, suppose there is a pressure P, this can be related with respect to rho into T. So if we know the ideal gas law, P is equal to rho RT. So there is rho, there is temperature T, R is the universal gas constant, and internal energy can be represented with I into I of rho and T. Okay, so where it is P is equal to rho RT, and where I is P into T, constant specific enthalpy. Specific constant for heat at constant volume into temperature T. Okay. All right. Now we come to the Navier-Stokes equation for that's very important equation. So anyone can tell me that what's the difference between Navier-Stokes and momentum equation? Why we have to derive Navier-Stokes and momentum equations? If you have seen the videos Prof has discussed. Mother,
So yeah, the difference between Navier-Stokes and Euler equations.
momentum equations. Navier-Stokes and momentum equation.
Uh, I don't recall that actually.
Anyone else can think of that? Okay. So let me first write the heading. Navier-Stokes equation for Newtonian fluid. Navier, these were two scientists. Stokes equations for a I will tell when I will write it completely. Then you will understand. Then you will appreciate why these were two terms. So Navier-Stokes equation for, you can say, uh, let me write for in a complete way for a x1 of the direction, either x, y, or z. So everything has been derived, but I'll just write the row of, again, the left hand side term. The row of du by dt is nothing but first term is pressure term. First term is pressure term minus dou p by dou x plus dou by dou x. This is I'm writing as a general for a compressible flow as well. Dou by dou x plus 2 mu dou u by dou x plus lambda of divergence of u, because we are writing for x direction. Let me write here x direction plus dou by dou y mu dou u by dou x plus dou v by dou x. Everything has been derived in the lecture videos. Dou by dou z of mu into dou u by dou z plus dou w by dou x plus source terms. Now, if you observe this equation, carefully observe this equation and the equation which I wrote for momentum, this equation, there is one huge difference. If you see, there is a variable u, there is a variable p, there is a variable tau. Equation has three variables in one direction itself. But if you see this equation, there is a variable u, there is a variable p, and then again there is a variable u, v, w. So I have eliminated one variable, that is tau, in terms of the velocities. That is why there was a need to reduce the number of variables, and there was a need for the Navier-Stokes equation. So there is no tau this time. Tau has been transformed in these ways. That has been derived itself. So that is why Navier-Stokes equation was used. So similarly for other directions as well, you can write. Okay. So similarly, energy equation is also there for Navier-Stokes. Okay. That is, let me write. Someone wants to join. Admit. Okay. Okay. All right. Yeah. So I was on describing about the energy equation by the little. So this is Navier-Stokes equation in vector notation. Let me write, or rho of dou u by du by dt is equal to minus dou p, the pressure term, dou p by dou x, divergence of mu grad u plus those terms. Okay. This whole big bracket is this, okay, in a vector notation. And similarly, for internal energy equation, for internal energy equation, rho of di by dt, I is nothing but internal energy per unit mass, specific internal energy. P, my negative of P, divergence of U plus vector U. This is not velocity. This is a complete vector U. Divergence of K grad of T plus the term phi plus some. Okay. So phi has a huge expanded value. which is already derived in the uh, equations. Okay, it's basically a dissipation function. Okay, dissipation function that's already been derived. Okay, and week 2. So this has been done in week 1 lecture videos. I'll just give a glimpse. Let me just give a glimpse. Those who have joined late. So I've generally basically talked about the glimpse or the recap of what has been done in the lecture videos by the prof. So we have discussed about the governing equations, which are nothing but mass conservation, momentum conservation, and energy conservation. So mass conservation is rate of increase of mass is equal to net rate of uh, mass of the flow of mass into the fluid element, and this is a general final equation in index notation. Sorry, index not vector notation as well for unsteady three-dimensional as well as for incompressible flow as well. Then how any rate of change of any property, which is the left-hand side term d phi by dt, but we want with respect to per unit volume. So this is per unit mass, this is per unit volume. And finally, substantial derivative of any property phi is expanded in this manner. Then we came up to the momentum equation because we did all this because there is a left-hand side term that is instead of property phi, there is a uh, another properties like UVW. So in the left-hand side of the equation, that is the rate of increase of mass of a momentum of a fluid of the particle is sum of all the forces acting on the particle. And the left-hand side term is written in the green, rho du by dt, and other right-hand side is sum of the forces, that is body forces plus surface forces. So this is an x direction momentum equation. Then we came up to the energy equation in the 3 dimension. So which is nothing but rate of increase of energy in a fluid particle, that is rho dE by dt. Again, from the property phi is being converted to energy E, which is nothing but net rate of heat added to the fluid element plus net rate of work done on that fluid element. So this is energy equation. And then we need equation of states because a lot of variables are there. So pressure can be written from gas law equation, that is rho RT, and internal energy I can be written as CV into T, specific internal energy. Okay. The Navier-Stokes equation was used so that uh, the discussed terms in the momentum equation, that is shear stresses terms, can be changed into the velocity terms. Okay, and this is for internal energy equation. Any doubts so far? Any doubts to anyone? Yes, no. Are you all there?
No, all good.
Okay, all good. Okay. So now we have understood all these equations. You might have seen all the proofs from the lecture videos. If not seen, go back, see, and always please come up by seeing the lecture videos. Now we will come to the questions. Very basic questions are framed on these things. So moderate to basic questions are there. So I'll give you a few questions one by one. Okay, we'll discuss. So most of the assignment questions are discussed in this lecture notes itself. Okay, everything is there in the assignment. If you see, that's a very pretty simple assignment. But I'll give you some numerical questions which are not in the assignment so that you are able to solve. And I'll give you time for each question. Okay. So given the Eulerian velocity vector field, that is V is equal to 3T I cap plus X Z J cap plus Ty square K cap. Now you need to find acceleration of particle. Find acceleration of particle. Just take a minute or two and try to solve it, please, and give me the answer. So if anyone has done, you can tell me.
So its answer should be in vector form, right?
Yes, yes, definitely. It's an acceleration, so acceleration is a vector quantity.
Sir, 3I plus y square plus 2y t x z k cap plus 3z t y squared x j cap.
Yes. And what about k
Uh,
cap?
Sir, k cap is y squared plus 2y t x z.
Correct. Right. Okay. So let's discuss right answer.
Thank
So
you, sir.
yeah, yeah. Brajadhar, right? Brajadhar, you are from which college?
Sir, NIT Calicut.
And BTech, right?
No, sir, MTech, sir.
MTech. Okay. All right. So solution. Let me write it down. So we have UVW components, okay, of this equation given to us. So U is 3T. U is, if you observe, U is 3T. V is XZ and W is TY square. Okay. So we know that the to evaluate the vector derivatives, we know that T dou of any property V by dou T is equal to I into dou U by dou T plus J into dou V by dou T plus K into dou W by dou T. This is a local part, then the other connective parts. So let me write d of acceleration is nothing but d v of dt is dou v of dou t plus dou of u by dou x plus dou of v by dou y plus dou of w by dou z, dou of w by dou z. Okay, so if you see dv by dt, this can be written as dv by dt can be written as dou u by dt I cap plus dou v by dou t j cap plus dou w by dou t. I'm writing this term. Okay. Plus dou w by dou t k cap. We know that only u and w are the components, are the values which dependent on time t. Dependent on time t. So this can be written as 3 I cap. This term will be 0 plus derivative of this is equal to y square k cap. Y square k cap. If you do dou w by dou t. Okay, this is dou v by dou t. Now the other terms, dou v by dou x. So if you do dou u by dou x, that is how much? Let me write it down. Dou dv by dt is nothing but d I cap plus y square k cap plus dou v by dou x. Dou v by dou x is how much? Z. Dou v by dou y is 2yk. Dou v by dou z is xjk. Okay, so let me write. So if you see in all each and all direction I was telling about, so the final answer will come out to be 3t into z j cap, okay, plus x z into 2ty k cap plus ty square into x j cap. Now rearrange I, j, and k terms all together. So I comes is only 3I cap. J terms has 3tz plus txy square j cap plus 2xyzt 2xyzt plus y square k cap. So any doubts to anyone here? So any vector velocity v is sum of the local part and the convective parts. Any doubts to anyone?
No doubt.
No doubts? Okay. All right. Now something I have missed here. Have I missed something in between in writing the equation? I think uh, I think I have miswritten this part. Let me some portion I have miswritten. U into dou v by dou x. Yeah. V into dou v by dou y plus w into by. Okay. If you see, u is nothing but 3t. If you do complete dou v by dou x, that is dou v by dou x is how much? Zj cap only. So 3t into zj cap. 3t into zj cap. Similarly, next term v into dou v by dou y. V is nothing but xz and dou v by dou y term is here 2ty. So xz into 2ty k cap. Similarly, the last term. That's how you have did it. Okay. All right. Let me the circles. Yes. All right. Next question I'll give you. So if you find any mistake or doubts, please point it out at that time. Question says that under what conditions, under what conditions does the velocity field, that is velocity field is v, is a1x plus b1y plus c1z I cap plus a2x plus c2y plus c2z j cap plus a3x plus b3y plus c3z k cap, where a, b, c, where a1, b1, c1, and so on are equal to constants, represent an incompressible flow which conserves mass. Okay, you all can try it. This question. If someone completes, you can tell me.
Yeah, A1 plus B2 plus A3 equal to 0.
Equal to 0.
Okay, let
Yes,
us
sir.
see. Yeah. So, can anyone tell me like how you did?
Sir,
Yeah,
del dot V equal to 0, like for
that,
incompressible field.
And why you did del dot v equal to 0, Madhav?
because it's an incompressible equation. So the density is constant. So there would be no time derivative of density.
Correct.
So,
Correct. Both of you are right. Okay.
Mm.
So it's a incompressible continuity. From the incompressible continuity equation, you know that divergence of the velocity vector field is equal to 0. Let me write solution. So you have for incompressible continuity from incompressible, sorry, from continuity equation, we know that divergence of velocity vector field v equal to 0. So that means dou by dou x of u plus dou by dou y of v plus dou by dou z of w equal to 0. You have u v w given as above. That is dou by dou x given x plus v1 y plus v1 z dou by dou y of v2x plus v2y plus v2z plus dou by dou z of v3x plus v3y plus v3z equal to 0. So if you do the derivative, dou by dou x of a1x is a1, rest other will be 0 because they are terms of y and z. Similarly, from another, first term 0, second term will be v2, and third term will be c2 0. So that is v2, and this first term 0, second term 0, third term will be c3 equal to 0. That's the condition. All right. Next question. Question says that incompressible velocity field is given by u is given as a to x square minus y square. V you don't know, and w is given as b. A and b are constants. We must form. We must use the form of the velocity component for finding out p. So you need to find p. Simple question. Go ahead.
Sir, minus 2ayx plus c1. C1 is very constant.
C1 is a constant. Is it a constant? Are you sure?
Sir, am I correct? Yes.
Will it be a constant or a variable?
Yes, sir. C1 is a constant. Like velocity is equal to minus 2ayx plus c1.
Sir, constant. C1 is a constant.
It will have a constant
Like
value.
I just del V by del Y equal to minus 2AX.
2xy first term is right, minus 2xy,
Yes,
correct.
sir.
But
If
it's
there
a
is a
partial
boundary
derivative.
condition, then I could
Carefully see, it's a partial derivative. So
plus
you cannot
C1. C1 is a constant. Plus
Yeah, so
C1.
it could be a constant
Yes,
in
sir.
x and z.
x,
मतलब,
z, and t also.
x, yes, okay. हाँ,
Because all these properties of a fluid are dependent on
Yes,
position as
sir.
well as time. This was
okay.
my first line in the lecture, right? Yes. Okay. So solution. So how we are doing is that continuity equation dou of
Yes.
dou x plus dou v of dou y plus dou w of dou z equal to 0. So u is a into x square minus y square. Dou of dou x
So
a
your
into.
video is, I think, perfect. Okay.
Hello, am I audible? Hello,
Yes, sir. Audible.
my video is visible. Am I
Yeah,
visible to you?
all good.
Yes, sir. Yes, sir. Now it's okay.
Okay. X square
Yes,
minus
sir.
y
Now it's
square.
visible, sir.
Yeah. Okay. Cool. Dou v by dou y and w is b. So dou of dou z of b equal to 0. So here, if you see, it will be 2ax. This term we need to find out. Dou v by dou y minus 2ax. Dou v by dou x. Okay. Dou v by dou y plus 0 equal to 0. Okay. Transpose it on the right hand side. You will get minus 2ax. And now you have to integrate the partial integration. So v is equal to minus 2axy plus any function of x, z, and t. It's not directly a constant. It's a partial integration because v is dependent. V is a quantity which itself is dependent on x, y, z, and t. Position, all the position and time. But here y has been already integrated. So other two dependent variables x and z and the fourth dependent variable that is time t will come in. Any doubts? Okay, no
No,
doubts.
sir.
Yeah. Okay. Next question. Let me review. So the I guess you are able to access the folder where the videos, oh sorry, the lecture notes will be uploaded. Did you got any link
Yes,
or
sir.
resource folder?
There are transcript of the videos and
Yeah, there might also be one link of Google Drive as well, lecture content related to where I have made two folders for so far. One is of books, all the books I have uploaded, the PDF. Three books I have uploaded: Patanka, Malala Sekra, and some Mulakkar. Yeah, these three books Prof has also suggested. You can check out. And week 1 folder where I'll upload these notes. Okay. Also, you will get the link for maybe for my YouTube videos, which is this session is being recorded. Okay. So that's why I'm saying. So it will be recorded and you can again see it at any point of time. So I'll write down my channel name as well here, even if you don't get the link. Okay. All right. Next question.
Where we find the notes, you said,
See,
of
there is
this
a
lecture.
column week 0, week 1 transcripts on your course profile on NPTEL, right? So one of the column will say,
Okay.
Madhav, can you uh, give him the guidance like
yeah, yeah. So basically, in the course outline only, there are the week 0, week 1, week 2 rows. So below that there is video download, text transcript, and books. वहीं पे कॉलम है उसी पे मिल जाएगा.
Uh, ठीक है, thanks.
okay, Brazil? Okay.
हाँ
Even if
हाँ
you
सर,
find
thanks. Yeah.
even if you find difficulty, you can mail the NPTEL team, or still they don't reply, you can ask me in the next. Okay,
Okay,
no
sir.
problem.
Thank you, sir.
But I'll share the what my YouTube channel name in the last, so that I'll upload after this class because this recording there itself.
Okay, sir.
Yeah. Okay. So notes is nothing but whatever the PDF I'm writing. I'll make a PDF for it. So now it's the same question. Now you have to tell me the question is in the continuation. Question is continued, taking the same velocity fields. So let me write a question is taking velocity fields field with b equal to 0. That is u was a into x square minus y square. V you have computed as minus 2axy and w is 0. You need to determine under what condition it is a solution. To Navier-Stokes. Navier-Stokes momentum equation. Assuming that these conditions are met, determine the resulting pressure when z is in up direction, when positive z is plus positive, z pointing upwards is plus, that is g of x is 0, g of y is 0, gravities, and g of z will be negative g because gravity acts downward. That's the question. Okay, go ahead and try to solve it.
Sir, del P by del X equal to 0, del P by del Y equal to 0, plus
Hmm.
del P by del Z equal to 0, plus GZ.
What you are telling, what is this?
Sir, it's coming equal to 0. Like, Del P by del X I got 0 from the first, after doing rho du by dt equal to minus del P by del X plus mu
Okay.
del square or u. From first I got del P by del X equal to 0, and when I next derivate in the rho into dv by dt, from that del P by del Y equal to 0,
Okay.
and after doing rho dw by dt, and then we are getting del minus del p by del z plus rho gz, and
Okay.
gz is z I cap.
Red I cap. Okay. So you didn't got any constants. You didn't find that you should calculate any constant or something.
No, sir, I actually solved these three individual.
Okay. All right. We'll see. Any other? Madhav, Bhavan, Jayan, Nitesh. Nitesh, are you there? Nitesh Prasad. Yes. Can you unmute?
So I guess the condition would be that it is first of all the steady. So all the time derivatives would be zero because the time का term नहीं है.
Okay.
And after that I was writing the equations only.
Okay. What about Bhavan? Bhavan, are you there?
I'm there actually.
Yeah. Are you able to get it that how we can solve this question?
For this question, no, I think I should go and watch some lectures and I should come back and see.
Okay. What about Jayant? Jayant, you are there? It's a good question actually. It's a lengthy and a good question. Bit lengthy. Take a minute more and think that how it. I'll give a minute more. Just have an idea that how we can go ahead with this. Yes, Reza, you want to say something? You want to change your
Um,
answer?
I will. I'm trying now, sir.
Yeah,
Just
yeah, yeah. Okay. See, this course is CFD with finite volume. I'll tell you guys that it's a very fundamental and a very great level of course that you give you an idea of how the all these equations get discretized, how the commercial software works at the back end. Okay, because we don't know what is happening behind an NSYS, what is happening behind another software. Some of the softwares are fluent, but if you want to develop your own codes or use the open source softwares like OpenFOAM and everything, you don't need to know how the equations are being discretized. And this is a very good course that will help you a lot to understand the basic mathematics and what's happening behind the equations. So if you regularly attend and continuously uh, like watch the videos, come to the tutorial session, ask me doubts, I also will feel very good, more motivated to teach you in a better way. Okay, so that's it. If you'll try solve your assignments, definitely you will understand this course. This course is not difficult. It's just that you have to be consistent with what's been happening. And every time there are only 3 to 4 videos, which you can see in maybe 1.5x as well if you have a time crunch. So all the transcripts comes there for every lecture. Yeah.
Sir, what can we take density value is equal to 1? Like
How does it
I'm
will
getting
matter?
now, sir, I'm getting minus del p by del x equal to rho bracket 2ax minus 2ay.
Okay.
So, yes, sir. If we like take
In it,
density equal to 1, then it may get shorter.
okay. Let's
So
see.
I'm
Yeah.
getting del p by del x is equal to minus of rho x 2a square and bracket में x square plus y square.
Oh. And Nitish is saying I think we should differentiate with respect to velocity in z direction. That's all fine. Okay. Let's see. Nitish, you are from which college? Are you doing a like you are studying or you are a working professional industry or something? And if you are studying, what you are studying from which college?
Sir, I'm a PhD student.
PhD student in which university?
Sir, IIT Roorkee.
IIT Roorkee. Okay. From which department you are?
Sir, hydro and renewable energy.
Okay. All right. Let us solve this. Let me turn on my camera. Yeah. Okay. Question. I think this might be our last question of the class. So it's a 2 hour sessions. Solution. Quiz. See, we know that momentum equation in all the directions. So let me write the momentum equation. That is rho into gx, body force, pressure term, dou p by dou x plus mu time viscous terms, dou to u by dou x square, dou to v, sorry, dou to u by dou y square plus dou to u by viscous term it is 2z square is equal to rho into du by dt. That was only the momentum equation for x direction. This is for x direction. Now put the values one by one. Gx is 0, so rho into 0. Dou p by dou x, you don't know. Dou p by dou x. Mu into second derivative of velocity u, that will be 2a. If you do a second derivative of this velocity, that will be 2a. 2a. Second derivative of velocity u with respect to y will be minus 2a. Put the value minus 2a. Second derivative with respect to z will 0. There is no z. It is equal to. Now this du by dt, we know that we can expand this term. How? This is nothing but acceleration. Dou rho u by dou t plus u rho dou u by dou x. Am I right or am I wrong? Sorry. U to complete v by dou x plus if you go with u or v, the question which you did the first question, dou v by dou y plus w dou v by dou z. This was the acceleration question, the first question which we did. You need to find the acceleration. This how dv by dt is written. That is the right hand term, the rho into dv by dt. So that is only I'm writing. Okay. So if you do all of this, so one by one, if you see, that will be 2a square
X.
rho into x cube. Just a second. Xy square. Yes. Please say.
Sir, can I tell my answer if you say what I
Yes,
got
yes, go
in
ahead.
del p by del x? So del p by
Okay.
del x equal to rho bracket 2a square x cube minus 2a square xy square plus 4a square x square y.
You are somewhat right. Let us see. You are somewhat right. Let's see. So yeah, first thing we are seeing that under what condition it is solution to Navier-Stokes equation. So just I am removing this and just putting it here. If you differentiate it and put it here, this will be the right hand side. Okay. This is your x direction. Okay, I think it will pass the page. I have to write it. 2 a square rho. It's just an expansion. I'm not writing each and every step. You can expand and write it down. Now for y direction. Y direction, similarly for y direction. You see that there is no point, you are not getting anything from here. So let us see y direction or whatever you have written. Let me write in dou p by dou x, what you are saying. Dou p by dou x is equal to mu into 0. This term is all 0. I will not write it. This is nothing but minus 2a square rho x cube plus x. This is dou p by dou x. Now y direction. Y direction. Rho, again rho into gy, that is 0, minus dou p by dou y plus mu into dou 2v by dou x square plus dou 2v by dou y square plus dou 2v by dou z square is equal to rho t dv by dt. Okay, so this is 0 minus dou p by dou y. Again do the second derivative of x velocity component v with respect to x, y, z. So if you do velocity component v with respect to x, y, z, with respect to x it will be minus 2, with respect to y again it will be minus 2. Okay, so it will come out to be, and with respect to z it will be 0. So it is mu time 0. And on right hand side again expand and do 2a square rho x square y plus y cube. So dou p by dou y from here is minus 2a square rho x square y plus y cube. This is dou p by dou y. Similarly from z direction, I'll just rho into negative g because gz is not 0 minus dou p by dou z pressure term. Again, if you do, that will be 0 and right hand side will be 0 also if you do that thing. So from here, now we can write it in a simplified manner, the pressure. So viscous term has vanished. Okay. Okay. And this equation can be represented as minus dou p by dou z is equal to rho into g. So pressure is nothing but minus rho g z, because it's a partial derivative. That will be function of x and y. There is no time term, steady. No time term, it's a steady, so that's why I didn't wrote the time term. It's difficult to partially integrate this term. Okay, that's why I didn't did. It's difficult to partially integrate this term. It is possible, but difficult. Okay. So with each and every direction, we did this, and we got from the z direction, pressure is minus rho g z plus function. So the pressure is hydrostatic in the z direction, which follows anyway the fact that flow is two-dimensional. Flow is two-dimensional. Now the equation is, if you see the equations, both the equations of the x and y direction, if you see the equations of x and y direction, this equation and this equation, okay, the given velocity field is the solution. One way is to find out, to form the mixed derivatives from this and separate them and compare them. Let us see from the equation 1. Let me name the equations as equation 1 and 2. So this is equation 1 This is equation 2. Let's see how we will do it. So differentiate equation 1 with respect to y. Okay. So dou to p by dou x, dou y will be minus 4a square. Why did with respect to y? Only a single dependent variable y is here. Single term of a dependent variable y. 4a square rho xy. 4a square rho xy. And differentiate equation 2 with respect to x. Differentiate equation 2 with respect to x. So that will be again dou square p dou x dou y, which is nothing but minus of dou by dou x of 2a square rho x. That was the term x square y plus y cube, which will give you negative of 4a square rho xy. Now both of them are same thing. Compare them. Compare both of them. These are identical if you see. The right hand side also come out to be, even if you compare, right hand side also come out to be same. So these are identical. So the given velocity field is an exact solution to the Navier-Stokes equation. And to find the pressure distribution from the equation, this equation number 3, from equation number 3, you put this value in equation 1 and 2. You put this value in the equation 1 and 2. Let us see. Because you exactly don't know now what this variable is. 1. It's a variable. It's not a constant value. So both of them are equal. It's an exact solution. Okay. So what can I say? Do from the what I was saying, substitute this equation 3 in 1 and 2. Substitute 1 and 2. So dou f1 by dou x will give you minus 2a square rho x cube plus xy square, and dou f1 by dou y, because it is a, this f is dependent on x and y. F is dependent on x and y. Dou f1 by dou y is nothing but minus 2a square rho into x square y plus y cube. Now you can integrate with respect to x and y as. So if you integrate this equation with respect to x, integrate with respect to x, what you will get? F1 is equal to minus half a square rho x raised to the power of 4 plus 2x square y square plus f2 y. Okay, because you are respecting with x, so y will be there. Okay, and now you differentiate this one with respect to y so that you can compare both of them. Differentiate with respect to y. Differentiate this with respect to y. So you will get dou f1 by dou y is nothing but minus 2a square rho x square y plus f2 of y. Now compare. Compare a and b. Suppose this is a, this is b. Compare. So if you see f2 dash of y, you got to be minus 2a square rho y cube. You got the f2 dash integrated, just one integration. So f2y will be minus half of a square rho y ki power 4 plus, now this time it's a constant because it's not a partial derivative, it's a definite derivative. Now it is a constant. Now you can put this value back into the expression you have for the pressure. Okay, the You put this F2 in here, now integrate it because with respect to y, and then put back into this F1 back into this equation number 3. So you will get your final solution. Therefore, pressure of x, y, z is nothing but rho gz minus half a square rho x to the power of 4 plus y to the power of 4 plus 2x square y square plus. So this is the desired solution. Any doubts? Any doubts? Any doubts to anyone? Hello?
No, sir.
Okay, so this was the way that how this question needed to be solved. Yeah, this was a pretty good question because there is a partial derivative. These are not definite derivatives. Okay, so we can end our session. It's already 8 and I can tell my YouTube, even if you get or don't, I don't know. But you will find the link definitely. Um, Let me see directly by coming to this. So the YouTube channel link is www.youtube.com/NPTEL without any space word. Okay, I'll post the video. All right. Any doubts to anyone for the session?
No, sir.
No doubts?
No, sir.
So we can end the session. All right. So I'll see you all in the next session.